Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to talk about how to interpret answers for derivatives and integrals. So being able to explain our answers in the context of a given problem, be able to understand what units should be applied, etc. And we did this with derivatives, now we're going to look at both derivatives and integrals. So the first thing we're going to look at is when I take the derivative, so d dx, of a certain amount, right? Well, that derivative is going to give us a rate. Just like slope is rate of change, if I take the derivative of a function, it's going to give me the rate of change of what's going on with the function, or whatever, it's going to be the rate at which whatever the y values are changing. For example, if water is being drained from a swimming pool, and R of t represents the amount of water measured in cubic feet that is in a swimming pool at any given time, measured in hours, then R prime of t would represent the rate at which the amount of water is changing. There's actually a mistake here in these notes. This should be d dt, because if our variable was t, then we would take the derivative with respect to t. So d dt of r of t would give us r prime of t. The units for r prime of t, right? So look at the units up above here for r of t, and think about, if you could think about how to figure out what the units of r prime of t would be. Well, the units for r of t are cubic feet, which means the units for r prime of t are going to be cubic feet per hour. Cubic feet just being feet cubed per hour. One way that I like to figure out units for derivatives, or when we take the derivative of a function, is just to think about the slope formula, or what the slope represents. Right? So slope is equal to change in y over change in x. Now, the derivative is the slope of a tangent line at that specific point. But I like to use this formula to help us figure out the units. So the slope is the ratio of the change in y to the change in x. So if I think about my units for the y value in our original function, well, the units for the value of y, or r of t, right, because that represents our y value, well, those are cubic feet. The units for the x's, or in this case the t's, were hours. So again, derivative represents the slope of the tangent line at a specific point. Again, slope is represented by change in y over change in x. So if we look at the ratio of the units of the y values of the original function and the x values of the original function, that can help us figure out the units for the derivative. So think change in y, change in x, and think about the ratio of what those units would be. Now, if I look at integration, right, so if I take the integral of a rate, and in this case, our rate function was r prime of t, well, that's going to give us, it depends. If it's an indefinite integral, that will give us, so if I take an indefinite integral of r prime of t dt, that will give us the original function, right, the r of t function. If I take a definite integral, so this is what they're talking about, from a to b of r prime of t dt, well, that's not going to give us the original function, right? It's going to give us this difference. So r of b minus r of a. And what that's going to give us is an amount of something, right? So if you think back to particle motion, if I take a definite integral of a velocity function, that's going to give us a displacement, right? It's going to tell us how far the object ended up from its initial position. In this case, with water being drained from a swimming pool, if I take a definite integral of the rate at which the water is draining, well, that's going to give me the net change, right? So it's going to tell me, okay, 50 gallons, 50 cubic feet of water have drained out of the pool, or 100 cubic feet of water have drained out of the pool. And that's what they're moving on to here. So if I take a definite integral of the derivative function here, which is the rate at which the water is draining, well, that's going to give us, So I had to pause the video while I coughed there. That's going to give us a net change in the volume of water from t equals A to t equals B. Just like if we were talking about a velocity function, if we take the definite integral of a velocity function, it will give us a displacement of the object from time A to time B. Let's go look at a couple of different examples. So here we're back to particle motion. This table represents the velocity of a particle at given values of t, where t is measured in minutes. You can also assume that this is a continuous function. So the derivative is continuous, which means the original function is continuous. I know they don't say that, but we're going to assume that. Part A says approximate the value of the integral 0 to 30 of v of t dt using a midpoint Riemann sum, and then using correct units of measure, explain what this value represents. So again, I think without even figuring out what the numerical answer to that is, we should be able to explain what that means. So two things to do: find an approximation of that using a midpoint Riemann sum, and then describe what that represents. There are units here, so make sure you use units in your answer. Okay, if I'm going to use a midpoint Riemann sum, I'm going to break this up into 3 intervals. Technically, you could just break this up into 1 interval, going from 0 to 30, but that would be a less precise answer than breaking this up into 3 intervals. So plus it's a good review of midpoint Riemann sums. So this integral right here, that's going to be approximately equal to, remember for midpoint Riemann sums, you're doing rectangles. So the base of the first rectangle is 10, right? Because our intervals span x lengths of 10. The height of each rectangle is going to be the y value of the midpoint. So we're going to be looking at these 3 y values. So 10 times 1.6 plus 10 times, covered it up and I couldn't see it, 3.1 plus 10 times 1.6 again. So this gives me 16 plus 31 plus 16. So approximate, which gives me an approximate value of 63. Now we need to figure out again, what does this mean in terms of the problem? Well, if I take the integral of a velocity function, that is going to give me the displacement. So 63 tells me that the object ends up 63 units, or in this case, 63 feet away from where it started at 0. So let's write that. This represents displacement. Which means the object, or the particle rather, ended up 63 feet away from its initial position at t equals 0. And again, this is in the positive direction. Can I squeeze it in? Sort of, yes. It's in the positive direction because our answer was positive. This does not represent total distance because we don't know if the velocity here changed signs at all, right? If it doesn't change signs, if the velocity was always positive, then this would also represent total distance. Now, we can say one other thing. We can say that this also represents net distance. Because net distance is equal to the absolute value of displacement. So if our displacement is positive, then displacement and net distance are the same. If this number was like negative 63, then that would not represent net distance because it was a negative number. Okay, let's move on to part B. Part B, let's see if I may have to do my work up above still. It says, what is the value of the integral 5 to 25 of a of t dt? And using correct units, explain what this value represents. So here, we are going to use the fundamental theorem of calculus. And again, I know the initial condition of the FTC says that this function right here, a of t, is continuous. We're going to assume that it is. I wish they had said that it was, but it doesn't, so we're just going to assume that. Otherwise, we wouldn't be able to apply the FTC. So before you listen to this explanation, think about how could you figure out this value using the FTC. Well, using the FTC, the integral from 5 to 25 of a of t, of a of t dt is equal to the antiderivative of a, which we know is velocity, so v of 25 minus v of 5. And fortunately, we're given all these values in the table, so it makes it very straightforward for us, right? So v of 25 is equal to 1.6. V of 5 is also equal to 1.6, which gives us 0. So the value of that integral is 0. Think about what this means. Does this mean that there's 0 acceleration? Does it mean something else? What are the units, etc.? Okay, well, what this means is that there's a 0 net change, or there's no net change in velocity from 5 to 25. Again, we are not doing part A. I'm just writing it up here so we can see the chart as well as the problem at the same time. So we can say there is no net change in velocity on the interval 5 to 25. Another way of writing this would be to say the net change in velocity on the interval 5 to 25 is 0 feet per minute. Again, and that's because if we look at this table, right, from 5 to 25, well, we start at a velocity of 1.6 feet per minute, and we end at a velocity of 1.6 feet per minute. So there's 0 net change. Now, that doesn't mean that the velocity is 0 on that interval. It doesn't mean that the acceleration is 0 at every single point on that interval. All it means is that over the entire interval 5 to 25, there is no net change in velocity, or the net change in velocity is 0 feet per minute. Now, had I chosen a different interval, our answer may have been different, right? Let's say I'd chosen the interval 0 to 20. Well, over that interval, the velocity, the net change in velocity would have been positive 2.4 feet per minute. Or if I had chosen some other interval, it could have been a negative net change in velocity. Now, let's really quick think about, again, the units for this. How do we figure out the units for what our answer to these integrals are going to be? Well, let's go back. Let's think about part A. Right? I have the integral 0 to 30 of v of t dt. The units for this answer were the units of the position function, right? Because what this is doing, right, to evaluate this, we're taking the antiderivative of v of t. So our units deal with the antiderivative of v of t, not v of t itself. The antiderivative being the position, or p of t, so our units would just be the units for p of t, which in this case would just be feet. So units would be units of p of t, or the position function. Now, if I look at an integral of the acceleration, again, it doesn't matter what my limits of integration here are. These units would be units. So units would be, it seems a little redundant, but we're just going to continue. Units would be units of v of t. Okay, so that's why our units there were feet per minute rather than feet per minute squared. So it may be easy for you to think about units for particle motion because we have become quite familiar with position, velocity, and acceleration. But when we get into other problems where, maybe we're dealing with temperature or we're dealing with money or something like that, just think about, okay, my answer to an integral, if I'm dealing with like a word problem, my units for that answer are going to be the units of the antiderivative. So you've got to think about one function before the function you're taking the integral of. Hopefully that helps. Hopefully that'll help you figure out what units are necessary for future answers. All right, let's see. We're going to at least do one more. All right, so let's talk about the temperature of water in a bathtub. So the temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is in minutes. So let's actually have you pause the video, answer question, all three of these. There's 3 questions here, and then join me back for a discussion. All right, so the first question says, using the data in the table, estimate the value of w prime of 12. Using correct units, interpret the meaning of this value in the context of the problem. Well, they're just asking us to estimate the value of a derivative, right, at t equals 12. This goes back to a couple units before this, right? if we're going to estimate the value of a derivative, which is the slope of a tangent line, well, we can use the slope of a secant line to do that. So we choose two values on each side of 12. So w prime of 12 is approximately equal to w of 15 minus w of 9 all over 15 all over 15 minus 9. And this problem, you would be allowed to use a calculator for this just to help you evaluate. And what is going on? This gives us approximately 1.017, depending on whether you round or truncate. Let's go ahead and put units here. We're finding a derivative, so this is not only going to be degrees Fahrenheit, it's going to be degrees Fahrenheit per minute. Interpret the meaning of this value in the context of the problem. Well, this value represents the average change in temperature on the interval 9 to 15. Or the average rate of change, the average rate of change in temperature. Now, it's an estimate of the rate of change in temperature at T equals 12. But it's not the exact value. It may be this value. It may be something else. All we know is that this is an estimate. What we do know is that this is the average rate of change of temperature over that interval. So a couple things we can write. Estimate of rate of change in temp at T equals 12. It is the average rate of change in temperature on the interval 9 to 15. So it's an estimate for the rate of change at T equals 12, but what we know for sure is that it's the average rate of change in temperature on the interval 9 to 15. Okay, moving on to the second one. It says use the data in the table to evaluate the integral from 0 to 20 of w prime of t dt. Using correct units, interpret the meaning of this integral in the context of the problem. Well, we are told that this function, if we go back up here, we're told that w is a twice differentiable, which means it's continuous, which is what we need to check off for us to use the FTC. So w of t is continuous, which means we can evaluate this using the FTC. So this would be equal to, w prime needs to be continuous, but we were told that this is a twice differentiable function. Twice differentiable meaning we can take the first derivative and we can take the second derivative. If we can take the second derivative, that means that the first derivative must be continuous. So w prime of t is continuous. Now back to how we evaluate this. We have w of 20 minus w of 0. We just look in the table for this. W of 20 is 71.1. W of 0 is 55.0. This gives us 16. Let's think about units, though. Because we are taking the antiderivative of w prime, that means our units are going to be units that are associated with w of t. In this case, that would just be degrees Fahrenheit. So what does this mean in terms of context of the problem? Well, it means on the interval 0 to 20, there is a net change of 16 degrees Fahrenheit. So on the interval 0 to 20, there is a net change in temp of positive 16 degrees Fahrenheit. I don't need to box that. If this was negative, then that would just mean that the temperature is decreasing by 16 degrees Fahrenheit, right? If it's positive like it is, then that means there's an overall increase in the temperature. Let's look at the final problem for this section. So it says for the interval 20 to 25, the function w that models the water temperature has a first derivative given by the function w of t is equal to 0.4 times the square root of t times cosine of 0.06 t. Based on this model, what is the temperature of the water at time t equals 25? Okay, so they give us the derivative, and we need to find the temperature of the water at t equals 25. Couple different thoughts you may have had here. You may have thought, well, they give us the derivative, so could we take the antiderivative and then substitute in 25? Well, that's a thought. However, this is not a very easy antiderivative to take, right? So that kind of is going to eliminate that aspect. Maybe you could try, but it's going to be pretty difficult to get that antiderivative correct. The other thing we could try is an FTC equation, right? So could we come up with a fundamental theorem of calculus equation, which just has one unknown, in this case, w of 25. So that is what we are going to do. Let's think about how to set that up. My interval is going to be 20 to 25. It's going to have the integral from 20 to 25 of w prime of t dt. And thinking about FTC, right, that's going to be equal to w of 25 minus w of 20. And again, we know that w prime of t is continuous on the interval 20 to 25. One, because it tells us up above, but two, because we could look at that function and there's no values where it's going to be undefined or not exist on that interval. This would be a calculator question. You may have been thinking, how am I going to evaluate this part on the left? Well, the answer would be with a calculator. I'm just going to substitute in what w prime of t is. I do not know what w of 25 is. That is what we are trying to find. But I do know that w of 20 is 71.0. So I'm going to have w of 25 minus 71.0 on the right-hand side of this equation. And now I've got to evaluate what I have here in blue. And again, that's just a calculator problem. Use a calculator to evaluate that definite integral. I end up getting 2.0432. I'm just going to go to 4 decimal places because I'm in the middle of a problem. And I think it's pretty clear to see how we're going to finish this off. Actually, I'll bring it up here. So I end up getting w of 25 is approximately equal to 73.043 degrees Fahrenheit. So the temp of water at t equals 25 is approximately 73.043 degrees Fahrenheit. So again, understanding how to use that FTC to set up an equation can make this pretty easy for us. I think we're going to leave it here. I think we've covered enough. We'll look at these other examples in class, but again, feel free to try them on your own. Try to break down. Really, the point of this lesson was breaking down the units and what the answers represent in terms of the context of the problem, right? We've done plenty of examples before on just evaluating definite integrals or taking antiderivatives. But now we're focused on what do those answers mean, right? What are the units? What do those answers mean in terms of the problem that I was given? Okay, as always, enjoy the rest of your day, and we will look forward to seeing you next time.